You're watching City Channel 4, your window to our community.
It's my delight to be here. I want to take all of us on a little tour of the kinds of things that we're observing and discovering in the universe through scientific exploration, and then allow ourselves to kind of think a little bit beyond the science. What does this imply? What kinds of questions does this bring up? How do we approach these discoveries as we contemplate what it means to be human? And things of that nature. So I'm speaking tonight from my own personal point of view. I'm not representing any particular organization. And so we will get started here exploring galaxies, stars, planets, and life, our dynamic and fruitful universe. If you don't take away any other message tonight, I want you to at least take away a recognition that our universe is amazingly active and beautiful. It is not stagnant. With modern telescopes, we can see fabulous detail. So this is an example of a star-forming region in our galaxy where you can see not only the interstellar clouds and dust, but the stars that have recently formed out of this material. Star formation is an active process. It's beautiful. I'm privileged to be able to work with telescopes of different kinds, telescopes in space, telescopes on the ground, astronomers from all over the world who work with different kinds of telescopes to answer and investigate different kinds of questions we have about the universe. But as was mentioned earlier, that's not where I started out. I started out here. I'm the one in the middle here. This is about let's see, we're in kind of eastern Iowa right now, kind of central eastern Iowa. This is approximately 2 states below here, south, north central Arkansas. This is the farm I grew up on in the Ozarks. It's a very cold day here in January, so we're feeding our cattle. And I got my start growing up out in nature, and I think that really got me interested in science because we didn't think of it in that connection, but just being outside days and even nights, I got to explore meadows and streams and forests, and I loved animals of all kinds, still do. And also, we had a pretty dark night sky. I mean, that's a rare treat these days. A lot of people don't get to see a really dark night sky anymore. But I got to see it many nights walking out at night. And it's, you know, that tangible connection with something bigger than you that really can lift your eyes and your mind. And I was able then to wonder what it would be like to explore those stars that I was looking out and seeing from horizon to horizon. Have any of you ever been out to a really dark place where you could see stars? Anybody? Raise your hand if you've ever been in a really dark place. All right, raise your hand if you thought that was awesome. Yeah, okay, good. Pretty much an equal match. Okay, that's good. So, the advantage, though, of being able to look at the sky with telescopes, especially our modern professional telescopes, is we get above, we can see things with much better resolution. This is an example. This is a cluster of stars in our own galaxy. It's called Omega Centauri. You can differentiate star from star. I'm sorry, the lights kind of make it a little harder to see, but I don't know if we can darken them because they're doing some recording here. But I think you can get the gist here that stars are different from each other. This is a very congested area of stars. It's much more crowded than the region around our own sun. And so we see a lot of stars, and given the tremendous angular resolution of the telescope that took this image, which is the Hubble Space Telescope, it's above the atmosphere, so it can get very sharp images, and that means you can differentiate star from star in a dense cluster like this, Whereas with a telescope on the ground, below the atmosphere, the turbulence in the air can blur the light, and we might see all this light kind of blurred together. But since we can differentiate star from star, you can see that stars are not all the same. You can see that they're different colors, reds, blues, yellows, greens. But you can also see that they're different brightnesses, and scientists will tease out the different populations of stars in a cluster like this and learn something about the formation history of the cluster and also something about its age. But we can also look at this and tease out something that's not really a scientific term, but we can see that it's beautiful. And to me, it looks like a collection of gemstones. So from images like this, we can have a sense of awe and amazement. And just to kind of get you thinking philosophically, I have a quote from Kant, who said that two things continued to fill his mind with ever increasing awe and admiration. Those two things were the starry heavens above him and the moral law within him. And this quote is, as I understand it, written on his tombstone, and it's roughly translated here. I think it's an interesting quote because I think these are the kinds of things we still think about in society today. We are still interested in the cosmos, where we fit into the universe, both on the very large scale and on the very small scale, as we delve into things that are much smaller than human eyes can see unaided. And then we're also questioning things about justice and morality, and where do these concepts come from? Why do we all have a sense of right and wrong, even though across cultures it may be expressed or understood in different ways? But where does that sense of the moral law come from? C.S. Lewis himself was drawn to faith as an adult when he recognized that everybody seems to have a sense of fairness. That's not fair. So we're all contemplating justice and who gets to make those calls, who decides what's just and unjust. These kinds of things are still a big part of conversation in our world and our cultures today, along with science. And of course, the third realm is what's happening in the latest lives of the movie stars and the TV actors, but Kant didn't know about that. All right. So first take-home message is that the universe is beautiful. Not a scientific term, but one we all can kind of understand. This is a region of sky taken as an image with a ground-based telescope, a very good telescope, gets a broad field of view. So different telescopes have different strengths. The ground-based telescopes can often get a much broader field of view, see the context of things, and yet, as I mentioned earlier, telescopes on the ground can often be hampered by the fact that they have to look through the Earth's atmosphere. Telescopes very high on mountaintops, or even better up in space, can often get above the atmosphere or much of it and see more clearly, but a lot of times telescopes such as the Hubble Space Telescope have very small fields of view, so they don't see the bigger context of what they're observing. And different telescopes observe in different wavelengths or colors of light. Some observe in the visible light bands that we see with our eyes. Some are better at seeing infrared light or ultraviolet light or X-rays or radio waves. And we need all this kind of information as astronomers to integrate together in our understanding of what we're studying. Things in space tend to radiate most of their light and information in wavelengths or colors that are outside of our visual bands of light. So that's why it's such a blessing to have telescopes now that are sensitive to these other colors and wavelengths of light. But this is an image of a region of the sky known as Orion. I hope you all recognize this. I should get my little pointer out while I'm thinking of that. So this is a famous constellation. You can see up at the top the big red star that's known as Betelgeuse. It's a big red giant thing. It's unstable. It will probably explode any day now within the next few hundreds of thousands of years, probably. So something of that nature. We're not quite sure. So get your affairs in order. This is Rigel down here. Actually, when it goes, whenever that happens, it's probably not going to be disruptive to Earth, but it is going to be a spectacular sight in the sky. All right. So what I want to call your attention to is this region down here. This is Orion's belt and sword. And if you look closely, even with binoculars on a clear night, you can see that some of these stars actually look a little fuzzy, and astronomers call anything fuzzy a nebula. All right, so we see fuzziness around this region and this region. Down here you see a kind of a colorful region because this particular telescope is also sensitive to some of the redder colors. If we zoom in on that region with a telescope that can get a higher resolution but sees a smaller field of view, we can see more detail there. So we're going to zoom in on this region with the Hubble Space Telescope and see what it shows us. So with this better telescope, but that sees only that small field of view where the reddish colored nebula is, we see this. All right. So this is the Orion Nebula. All right. It's a beautiful lit up cloud of interstellar gas. It's lit up into these delightful colors by massive stars that have recently formed out of this gas. So this is an active stellar nursery. When stars form, they shine their light back into the surrounding cloud of gas out of which they formed. And the most massive stars shine very brightly and very energetic photons of light into the surrounding gas. And those photons can hit the atoms in the gas, temporarily ionize them, which means separating the electrons from the rest of the atom. And when the atom recovers from that, it releases colorful light. So we can look at these different colors and assess what kinds of atoms are making up this interstellar gas. Most of it is hydrogen. And in fact, all a star is just a little pocket of this turbulent gas that's in interstellar space. It fills most of the volume of our galaxy. But if you get a little eddy that actually has a higher density than most of its surroundings, the density of that clump of gas can actually cause it to collapse by its own weight. Gravity just tends to pull things together. If you get enough mass in a small enough volume, that collapse of gravity will dominate over the turbulence that tends to try to disperse the gas. So once you get enough mass collapsing in on itself, you have what could become a star. If you have enough mass, it will collapse with enough pressure on the interior of that clump that it can spawn what we call fusion, where the hydrogen atoms, again, most of the gas is hydrogen, the hydrogen atoms will go through a process called fusion in the core of this clump of gas. The hydrogen atoms fuse, they form helium, and that reaction produces a photon of light as a product. And when that photon finally makes its way out of that condensed clump of gas, you have starlight. That's all a star is. So star formation is a pretty straightforward process, actually, and it's very active whenever we have dense interstellar clouds. Now, when astronomers see these beautiful, colorful nebulae around the galaxy and even in other galaxies, we say, aha, recent star formation has been going on. And in fact, massive stars are forming because it takes the bigger stars, ones bigger than our sun, to actually be able to produce the photons energetic enough to ionize the gas. So we know this is a signpost of recent star formation. After a while, the radiation and the winds that come from these stars actually blow away the rest of the tenuous gas in the region, just leaving the stars behind. So that's why we know if there's still a lot of gas left that the stars have formed only recently. But it is beautiful, right? The lesson of this segment is that the universe is beautiful. And we see many of these interstellar clouds. They're majestic. They also have a lot of dust in them. They often have these pillar-like structures which are formed when stars themselves, as they form, let's say off to the right-hand side of this image, begin to exude these winds and radiation, and those winds and radiation can actually carve out structures in the surrounding gas as it's blowing it away, because the denser material will hang on the longest. So if you have some dense clumps of gas, they'll hang on, they'll shadow the material behind them, and so you get, for a little while, these kind of long shadowed columns of dusty gas, and they make quite interesting visual features. But they're also interesting regions to look for subsequent star formation, because if this is the densest gas that's hanging on the longest as the winds from the recently formed stars carve out these structures, then that's the gas that's most likely to be able to produce more stars. And lower mass stars, like our sun, take a little longer to form. So we look in regions like this, where we know massive stars have already formed, bigger than our sun, but we know that lower mass stars may still be forming. Here's another region in the Orion region of the sky. This is called the Horsehead Nebula. Now this image was taken with an infrared camera capability on the Hubble Space Telescope, and you can see this kind of ethereal emission that comes from the dust in this region, and to me it's quite, I don't know, I call it kind of quieting to my spirit. Maybe, I don't know if you feel that way. To me, this doesn't look like a horse, this looks like a dragon. So you can interpret this as you wish, all right? Now these nebulae and the stars that form within them fill the volume of what we call galaxies. So this is an example of a spiral galaxy. It's just a kind of a random spiral galaxy that I pulled out of an archive of galaxy images. But you can see the beauty in the galaxy structure. In this case, it's a spiral, so it has these kind of spiral structures that form over time as the galaxy rotates. Most of the volume of the galaxy is filled with gas, these gas clouds, but there's a lot of mass in stars embedded in these spiral arms and gas clouds. There's so many stars toward the center that the light all blends together, and you just see this kind of whitish, bright color toward the center of the galaxy. You can also see background galaxies here if you look closely. To me, this is just a beautiful example of a spiral galaxy. We believe our own galaxy that our sun is in is a spiral, something like this. But we can't get all the way out of it to take a picture of our own galaxy. So we have to make do by looking around from within the plane of our galaxy and deducing its shape, and also looking at other galaxies. Now, astronomers found this to be so strikingly beautiful, such a beautiful example, that they named this galaxy NGC 1309 to kind of lift the spirit. We need poets to help us. Yeah. And we need artists to help us. So this is an artist's conception of our own galaxy, because as I said, we can't get all the way out yet to look back at it, with all due respect to Star Trek. This is where we believe our own sun and solar system lies about 2/3 of the way out toward what may be the edge of the galaxy, more or less, from the center. And we think that our solar system lies near one of the spiral arms. And so we can look around. In fact, if you go to one of these dark places I mentioned before at night and have a clear night and you look up, you can often see a kind of whitish glow across the sky. Has anybody seen that, this strip of the Milky Way? So what you're seeing is, by looking from our platform here toward the plane of our galaxy, which is, think of it like a pancake, kind of flat. When you look toward the plane of our galaxy, all the starlight that's kind of blending together, coming toward us, kind of blends into this whitish glow. So as you look toward the thick plane of the galaxy, all that starlight kind of lights up, and that's why we call it the Milky Way. It's like a path of milky white light. If you look in any other direction, off the plane of the galaxy, you don't see as many stars and you don't see the Milky Way. We also, by the way, believe that the center of our galaxy, and probably most other galaxies, contains something called a supermassive black hole. This is an ultra concentration of mass. It's so massive that light cannot escape from that region. So how do we know it's there? We can't see it, but you can certainly see material right around it. And as material is orbiting the center of the galaxy, you can get a handle on how much mass is in the center of the gas and stars orbiting the center of the galaxy. It's a pretty simple calculation, and the only thing that can account for the fast orbits of material around the core of our galaxy is a supermassive black hole. All right, so what do we use to do these kinds of observations? Well, we use telescopes, telescopes on the ground, telescopes in space. Telescopes are like, to me, a symphony orchestra, where different kinds of telescopes are like different kinds of instruments in the orchestra. They give us different kinds of information, and then we use all that together. We integrate it to get a better sense of what we're studying. How did we get to this point? Well, this is a graph that kind of shows you the progression in telescope technology over the last few centuries. So if you look from left to right here, these are years of observations from the early 17th century to modern times. And so you can see that Galileo is here. Galileo pointed a telescope at Jupiter and recorded the motions of little white lights right around Jupiter. And it turned out to be the moons, the 4 inner moons of Jupiter orbiting. And this was transformational in our understanding of the dynamics, not only of the Jupiter system, but by extrapolation to the solar system as a whole. What's on this axis is the sensitivity of these telescopes that are being used over what you could just see with your naked eye looking up. So Galileo's telescope was pretty good. It enabled him to record these kinds of observations of things that hadn't really been noticed before. And over the years, as eyepieces got better, as telescopes got bigger and better, this sensitivity improvement got better by leaps and bounds. Each one of these little tick marks, this is a logarithmic scale, so each little tick mark up on the scale is 10 times better than the one below it. So we're really moving orders of magnitude better in sensitivity. By the 19th century and early 20th century, photographs were being taken through telescopes. That allowed you to record light over time much longer than your eye could just understand something by staring through the telescope. That enabled us to really see more and more of what we now know are other galaxies. And then by going in to electronic recording, we got much more sensitive and accurate recordings through telescopes, CCDs and so forth in the 20th century. We went to space with the Hubble Space Telescope in 1990. That took us leaps and bounds, orders of magnitude more sensitive by getting above the Earth's atmosphere. And then the Hubble telescope has been serviced by astronauts several times, putting in new instruments and even improving its capabilities. The last servicing mission was in 2009, servicing mission 4, or SM4. And with that mission, new instruments were installed, and that took it off the charts here. So with that telescope, and there are other telescopes in space and on the ground that are getting better and better, we're able to see much more detail in the universe. So this is an example of how technology, I think in this case technology used for something very positive, has enabled science, and science is enabling some of the deeper questions that come from that science, the philosophical questions, the theological questions. What does it mean that we're discovering many, many galaxies and many, many planets outside our solar system, as I will discuss later? It's also quite rewarding when you can have people working together. In this case, scientists, engineers, astronauts, politicians, taxpayers, writers, enthusiasts, students, people around the world interested in getting telescopes to work and giving us information about who we are as one human family in this vast universe. All right, so the newest camera on the Space Telescope has given us this image I started out with of Omega Centauri cluster in all its detail, but it really helps to see these things in context. So let's kind of pull out a bit and go and look toward the center of our galaxy with a telescope on the ground. This telescope on the ground gives us a sense of lots of stars as we look toward the center of our galaxy, lots of dust and gas as well. Some of these stars, it turns out, are actually not individual stars. They're actually these dense clusters, these globular clusters. So we're going to zoom in now from what this ground-based telescope can see with its broad field of view and zoom in to what the Hubble Space Telescope can see in this region, and thereby giving you a sense of context. There we go. All right, this is I don't like this violent constellation, but it's the Centaurus constellation. We're zooming in and we're transitioning now from the ground-based telescopes to the space-based Hubble telescope. And what looked like an individual star now turns into this amazing cluster. Do you see why we need different telescopes to give us different perspectives? Some people like to see that again and some people don't. Which are you? Okay. All right, we'll do this again. All right, Centaurus. We're zooming in. We thought it was a star, but nope, it's a globular cluster of stars, many stars. And then let's transition to the detail we see with the Hubble Space Telescope. And there you have it. We're also now tracing the motions of these stars. These stars in this cluster are not sitting still. I mean, think about it. If they were, they'd all just collapse in on themselves because of gravity. So they have motions, and we're tracking those motions. All right, so that brings me to my next point, that the universe is active. It's not stagnant. All right, I've already said something about star formation, but even in our own solar system, we see activity. You all recognize beautiful Jupiter here. Jupiter is a gas giant planet, many bands of atmospheric gas and gases moving in different ways, juxtaposed next to each other. But for a long time, we've all been fascinated by this great red spot, which we know is a huge storm. It's much bigger than planet Earth. It's a big storm. But the Hubble telescope has been observing Jupiter for quite a long time, and the other planets as well, for decades. And so we can look back over and over, and what we've noticed is that spot is actually shrinking, and new little spots are coming out. So we know that the weather on Jupiter changes. Here's a classic image. You may recognize it, the Eagle Nebula. This image was taken in 1995. There was another imaging of it in 2014 with a newer camera on the Hubble Space Telescope that has more sensitivity, a broader color range, and a broader field of view. So you can see a little bit more about this region here. This is one of these interstellar nebulae, interstellar clouds that I mentioned before. You can see the pillar-like structures, again, that are carved out when massive stars that have recently formed begin to send their stellar winds back into their environment, blowing away the less dense gas and dust and leaving behind a little longer the denser material. And of course, it's in this denser material where new stars are most likely still forming. But we would like to see into these pillars, but we can't because they're dusty, and that dust itself is blocking our view into the pillars in visible light.
How big is that pillow?
Sorry? How distant is it? That's a good question. I would really have to look that up, but we're talking probably something like a light year across. So it's quite a big span, but I'd have to look that up to find out for sure. But what's interesting, looking not just lengthwise, but looking into it depthwise, is looking in the infrared. All right, so this new camera on Hubble can see not only visible light, but can see infrared light. It can see through some of this dust a little bit. So that's what we're seeing here. On the left is the visible light image. On the right is the infrared image that sees through a lot of that dust. So we see a lot more stars over the whole field because that veil of dust covers the whole region. And you can even see into the pillars a little bit. So this is the exact same region, just looking in visible light and infrared light. And you can see that there's a lot of activity, sometimes at the tips of these pillars, because again, those are very dense regions. That's why they're still sticking around. And of course, that's the most likely area for new stars to form. So you see them heating up in infrared light. It's heat light, infrared light showing up in some of these regions. If you're a good audience, when you leave today, I'll let you go home with your own image of the Eagle Nebula in visible light and infrared light. Here's another star-forming nebula, and here you see a stage that baby stars seem to go through as they form. Not only does material fall in on them, but some of it gets caught up in magnetic fields around the star and actually gets ejected out the poles of the star very energetically. It's kind of counterintuitive. But these outflowing jets are a common sight in baby stars as they form. And again, it takes, for a star like our sun, it can take millions of years for it to fully form. So we don't watch a star form from beginning to end. We see stars at different stages of their formation. This image was released last December because it was thought that this looked like a lightsaber, and it was released right when the newest Star Wars movie was released. A double-bladed lightsaber, but you can actually look closely and see several other jets because there's several young stars forming in this spectacular region. All right, so again, the theme here is that the universe is active. Here's going back into the core of the Orion Nebula, but we're going to look a little closer now. So we're back in Orion. These are those massive stars that are kind of lighting up the whole nebula. But if you look really closely at this image, you can see something else going on with the other less visible stars and features. And I'm going to blow up a couple of them here. So here's a couple of little darker dots here. And if you blow them up, you see some interesting things. These are heating up, collapsing little balls of gas, trying to form stars. It's hard because they're trying to form out of the remaining gas, but they're being pummeled by these winds and radiation from the massive stars that are already formed. So it's not clear that these objects will be able to completely form into stars. But they're getting hot. You can see them. But you see this interesting dark material around the protostar. This dark, dusty material is just that. It's dusty debris. You can see them in different orientations. This one's kind of face on, and this one's kind of edge on from our vantage point. The diameter of these disks is about the diameter of our solar system. So it turns out that stars that are forming these days, almost all of them seem to form with these disks of dusty debris forming along with them that are apparently planet-forming sites. And this is now a very hot topic in astronomy. Here's another one of these circumstellar disks that you can see in much greater detail around a young protostar, which is buried down in here. You can't quite see the star, but you see these disks, this disk that's actually carved out into ring-like patterns. This image was taken with a telescope that's actually an array of radio telescopes in South America called the Atacama Large Millimeter Array, ALMA. And it's showing us in these wavelengths of light that are very sensitive to the dust, the hot dust around a forming star, that this disk is very present, right? You can see it there. And not only that, the gaps and rings may indicate planets forming in there, because we know orbiting bodies can carve out gaps in rings, similar to how the rings in Saturn are carved out because of the dynamics of the moons orbiting Saturn. It's not clear yet whether or not there are planets carving out the rings here, but scientists are definitely looking into this with great enthusiasm. So planet formation is a hot topic, and it's an active process still going on around young stars. Back to our solar system, we see Jupiter even now is very active, gorgeous. We can monitor not only the red spot, but the moons around Jupiter and the other planets, which I'll mention later. Older stars are active. We see older stars, as they start to run out of their inner hydrogen fuel, they become unstable, and this causes them to start releasing their outer atmospheres in vibrant ways. There's an old star buried down in here that you can't see, but it's releasing its outer atmosphere in an active pattern that's quite beautiful, right? And someone thought this looked like something. What do you think this looks like? Anybody brave enough to say? Right. All right. Somebody cheated, but it's the Butterfly Nebula. That's right. Maybe you didn't cheat. That's good. Good guess. And it does look exactly like a butterfly. Here's another older star, but it's a big star, much bigger than our sun. And as it becomes unstable and releases its outer atmosphere, it can become so unstable that it actually explodes. So this is the debris of an exploded star. It's called the Crab Nebula. The different colors indicate the different kinds of material in the gases that are being expelled, and that's a key point we're going to get to here. The star, while mostly made of hydrogen, begins to fuse these heavier elements like helium, but not just helium. The fusion process carries on into producing heavier elements like carbon and oxygen and nitrogen. This can then be expelled back into the interstellar medium when the star explodes, and the explosion itself and the processes that lead up to it can create still heavier elements down the periodic table. And that gets dispersed into the interstellar medium, and it can get caught up in the next generation of stars and their planets that form. Now, this particular stellar explosion is of interest because it was observed and recorded by astronomers around the world about 1,000 years ago, mainly by sky watchers in China. They recorded that this certain star began to brighten up spectacularly in the sky, and we can still see the debris, as we see here, from that stellar explosion. So that's a quite interesting beacon in the sky. Here's another debris region of an exploded star. If you look at the star field, you can see this kind of purplish gas around it. This is the remnant of a supernova, the stellar explosion. And we can look at it not only with the cameras, but we can look at it with what we call spectrographs. So the little circle there is just to point your eye to some random place in this debris field. It could be anywhere in there, but if we want to study what it's made of, we have to use a technique we call spectroscopy. So spectroscopy takes the light that we're looking at and spreads it out like a prism into its constituent colors. And from that, you can learn more about what's emitting that light. In this case, by taking light from that region that was circled and spreading it out into its colors or wavelengths, you can see that at most of these colors or wavelengths, there's not very much brightness, there's not very much light. But at a few of these colors or wavelengths, you see a spike up in the brightness. And these patterns are emitted in very specific ways by the atoms or the components of that gas. So in this case, a spectroscopist can look at the spectrum and say, aha, that's the pattern of carbon, the red lines, or oxygen, the blue lines. So here we can tell something about what was produced in that star and what's being expelled into the surrounding medium. And what's available then for the next stars that form, they'll have not only hydrogen, but they'll have trace amounts of these heavier elements. And it also enables, in some cases, now we see the formation of these solid regions of debris in the region around the star as it forms. All right, we have activity even on the scales of galaxies. So here's our beautiful galaxy I mentioned before, but whole galaxies can be active. In some cases, they can merge together. Here's two that are being drawn together by their mutual gravitational pull. It turns out that merging of galaxies is very common in the history of our universe. We think about the expansion of the universe as galaxies being pulled apart, and that is indeed happening. But in regions of space and time, particularly in the earlier universe, when galaxies were close together, their mutual gravitational pull can sometimes dominate over that tendency to be pulled apart with the stretching of space. And it turns out that early galaxies in the universe were small and fragmentary, and over time, the merging of galaxies built up into bigger and bigger galaxies. When galaxies merge, they don't have a lot of collisions of stars with stars because most of the space, most of the volume in galaxies is pretty much a vacuum or with this tenuous interstellar gas. But it can disrupt and will disrupt the spiral structures of the individual galaxies involved and create a lot of turbulence. Here's a couple more galaxies that are a little farther along in that merging process, and you can see how they've lost their individual structures somewhat. They're going to form one galaxy eventually, but all the turbulence is spawning all kinds of active star formation, bursts of star formation. you can tell by looking at these colorful nebulae. And remember I said earlier, when astronomers see a colorful nebula, they say, aha, recent star formation. Now you may say, wow, this is all well and good and so interesting, so far away. Just a couple of years ago, by doing very careful measurements and observations, astronomers determined that our nearest neighbor, big spiral galaxy to our own, so our Milky Way is a big spiral galaxy, our nearest neighbor, grand spiral, is the Andromeda galaxy. It's about 2 million light years away. Andromeda and Milky Way seem to be on a head-on collision course. All right? So that's another reason to get your affairs in order. However, as I mentioned, there's not too many star-to-star collisions, at least that's what our computer models tell us. So really, we might be okay. We just might have a very different looking night sky in a few billion years, okay? And we have something else to worry about first, because our sun may start to burn out before then. But, you know, we'll worry about that when that happens. All right. So we've got a beautiful universe, an active universe, and finally an enormous universe. The universe is enormous in both space and time. Let me just try to give you a little sense of that. Here's our galaxy again that I keep pointing out as an example galaxy. But it turns out we now know, thanks to a hard work of astronomers, especially over the last century, that there are a lot of other galaxies outside our own galaxy. This is the Hubble Space Telescope's ultra deep field. It's my favorite thing the Hubble's ever done. And this is a product of looking at a small patch of sky with the Hubble telescope for several days, just collecting light so you could see the faintest things possible. There weren't many foreground nearby stars in this patch of sky to kind of flood the view. So what was glimpsed were galaxies outside of our own galaxy. And in fact, every little blip of light here, except for a couple of foreground stars like this one, every little blip of light here is another galaxy outside of our galaxy. So each tiny little thing here. And imagine that many, many of these galaxies could contain hundreds of billions of stars, each one. And this is only a tiny soda straw area of the sky. Imagine this extrapolated over the entire sky. That's the universe we live in, right? And if we could put our own Milky Way in the picture, it would look like one of these little spiral galaxies here, all right? And each one of these contains hundreds of billions of stars. There's no words to really describe this. You have to kind of see it visually. You can try to imagine and extrapolate. If you do, it looks like there may be a few 100 billion galaxies in our observable universe. But those are numbers that are hard for us to digest. And there's also a third dimension here, right? We see all these galaxies at once in the picture, but some of them are much farther away from us than others. And if you can tease out those distances, you can see some of these are much farther away, so they're farther back in time. It's taken time for the light to get to us from all of these galaxies, and it's taken longer from the more distant galaxies. So when you look at the more distant galaxies, you're seeing them as they were farther back in time. These images are astounding. They catch the attention of everybody. Here's the latest version of one of these deep fields, and it made the cover of USA Today a couple years ago. It even made the Huffington Post, which isn't normally reverent, but here it is. Some of these most distant galaxies are very interesting. You can hardly see it here, but if you blow it up, this little red blob, which doesn't look like much, is interesting. It doesn't have that big spiral structure. It's quite small. It has much less mass than our Milky Way. But it's interesting because it's one of the most distant galaxies we've ever seen. We're now seeing galaxies from such a distance that it's taken over 13 billion years for the light to get to us. So we're seeing these baby fragments of galaxies as they first began to form out of the beginnings of our universe. We think the universe had a very energetic beginning about 13.8 billion years ago. The fact I can even say that is amazing, but different telescopes and different methods of deducing this all are pointing to kind of the same conclusion, that our universe had a spectacular beginning about 13.8 billion years ago. And we're now seeing baby galaxies from within that first 0.8 of the 13.8 billion year history of the universe. This is kind of what graphically that looks like as we look deep into space and time. As our telescopes are getting better and better, that's what this is supposed to represent going down here, telescopes and instruments on the telescopes getting better and better, we can see fainter and fainter objects in space because our telescopes and cameras are better. Well, seeing fainter translates often into seeing more distant galaxies, more distant, fainter galaxies. So that's what these arrows are trying to represent. We're able to see fainter and thus more distant galaxies. Well, if you can see more distant, faint galaxies, you're seeing farther back in time because, again, it's taken more time for the light to get to us. So if you look at this graph from right to left, this is a timeline. Off to the right would be the beginning of our universe, what's often referred to as kind of the Big Bang, this burst of energy, the beginning of time and space as we understand it. And then you can see a few 100 million years turning into billions of years, going from right to left. And so we now are in the present time here, about 13.8 billion years. But our telescopes are seeing baby galaxies that began to form toward the beginning of the universe. And we can compare galaxies over time. We can see mergers in the early universe. We can see how closer to our present epoch the galaxies are bigger. They've grown through these mergers over time. And they've also matured because the stars within these galaxies don't last forever, especially the big ones. They come and go, and they produce these heavier elements that get scooped up into the next generations of stars. The fusion from these stars creates heavier elements that enrich the galaxies. So the galaxies in our epoch of time have these heavier elements dispersed without. Carbon, nitrogen, iron, oxygen, things that we don't see in early galaxies. Over here we only see hydrogen and a little helium. Here's another pictorial just kind of pulling some galaxies out of the deep field so you can see the difference between galaxies that are close to us, closer to us in time and space, and see how visually they look different from the galaxies that are more distant from us in time and space. You can see visually how galaxies have grown and changed and become more mature structures, bigger spirals and so forth over time. So the takeaway here is that from all these observations that we're able to make with our modern telescopes, we have deduced that the universe has developed over time and changed, and it continues to mature and change with this sequential production of stars, heavier elements, and finally planets and the disks of this debris of heavier elements around young stars. And this provides conditions needed for life to thrive. Right? On at least one planet. We need these heavier elements that stars have produced over the 13.8 billion years of galaxies maturing over time. So we know that we need this material for life to thrive on at least one planet here. The fact that I'm sitting here in a carbon-based body, breathing oxygen and, knocking on solids here, we can thank our lucky stars for having all this material, right? I just thought of that. Wasn't that cool? All right. So what a wonderful thing. I mean, I think of stars as what I call them God's factories for creating these heavier elements. Does all of this imply purpose, all right? We see the progression of the universe toward being habitable for life. Does that imply purpose? I have just moved from the science, all right? So the science seems to be telling us this information. This is an inference that is not scientific, all right? This is an inference, a philosophical inference. And a lot of times it's not clear when scientists go from talking about the science to talking about a philosophical inference. And not just scientists, out in the public, everybody, right? Is there a purpose to the universe? Well, there's some interesting perspectives on that. You can talk to different people, not only in our own time, but throughout human history, and ask that question and get different answers. The psalmist in the Bible would say, of course there's a purpose. The heavens declare the glory of God. The skies proclaim the work of his hands. This is a beautiful poetic psalm. It goes on to say that day after day they pour forth speech, night after night they reveal knowledge. Yet they have no speech, they use no words, no sound is heard from them, and yet their voice goes out into all the earth, their words to the ends of the world. There's some message that's going out to the world from the heavens and the skies. Even theologian John Calvin said that astronomy is not only pleasant, but it's also useful. It cannot be denied that this art unfolds the admirable wisdom of God. 16th century theology. And we have hymn writers who have written famous hymns like How Great Thou Art. It says, O Lord my God, when I consider in awesome wonder the worlds thy hands have made. Notice the plural there. I see the stars, I hear the rolling thunder, thy power throughout the universe displayed. Then sings my soul, my Savior God, to thee, how great thou art, how great thou art. This is an inference from looking at nature and feeling these senses of gratitude. But the science doesn't necessarily dictate that kind of response. Other people can look at the same information and have a very different reaction, all right? Physicist Steven Weinberg says the more the universe seems comprehensible, the more it also seems pointless, right? So that's a perfectly legitimate reaction too, right? So you can look at the same information and have different gut feelings, different philosophical responses, different theological responses, and you know, no one is right or wrong in a scientific sense. In fact, there was this very interesting project, the Purpose Project, where several leading scientists, philosophers, theologians, public figures were asked the simple question, does the universe have a purpose? And so you can go to this website. This is run by the Templeton Foundation, templeton.org/purpose, and read the short essays that each of their respondents gave for their responses. And so you can see a kind of litany here of different responses. We have you can probably recognize some of these names. We have Jane Goodall down in the lower center saying certainly. We're saying Neil deGrasse Tyson in the lower left saying he's not sure. We have a professor of chemistry at Oxford saying no. Some saying yes, some saying maybe, some saying unlikely, some saying I hope so. So you get the gist here, right? The science gives us the science. But whether there's a purpose behind it all depends on who you ask and their philosophy of it all. And in fact, I'm going to see if I can do something very dangerous here, but run to the web, because I just want to read to you a little short snippet of some of these. Let's look at no. So Peter William Adkins is a fellow and professor of chemistry at Oxford. And I won't read this whole thing, but you can, all right? Just go to templeton.org/purpose and you can read all these essays. He says, in the absence of evidence, the only reason to suppose that it does have purpose is sentimental wishful thinking. And sentimental wishful thinking, which underlies all religion, is an unreliable tool for the discovery of truth of any kind. All right? So that's one response. Let's go way over here. John Hott, senior fellow, Georgetown University. Yes, the fact that we can ask such a question at all suggests an affirmative answer. The impassioned search for meaning, perhaps our species' most distinctive trait, is not a longing that lifts us out of the universe or that takes place outside of nature. We are, after all, as much a part of nature as roaches and rivers. So too is our thirst for meaning, all right? And so we can go on and on and on. I like, let's see, Owen Gingerich, the astronomer here. He says he's psychologically incapable of believing the universe is meaningless. He believes the universe has a purpose, and the great intellectual challenge we have of human beings is to get a glimpse of what that purpose might be. And then let's see what Jane Goodall here says here. She says, certainly, but let me first explain. And she goes on to explain what she views purpose to mean. So I think this is quite interesting array to show you that this is a philosophical question. So let's go on and say, and look a little bit more at some of these perspectives. Freeman Dyson, the physicist, said that it would not be surprising to him if it should turn out that the origin and destiny of energy in the universe cannot be completely understood in isolation from the phenomena of life and consciousness, and the design of the inanimate universe may not be as detached from the potentialities of life and intelligence as scientists of the 20th century, when he was writing, have tended to suppose. Interesting thought. Let me see. There was something, yeah, okay. What about the perspective of faith? This might be of interest to some folks in this room. I don't want to go into great detail about this, but the question is, can science and religion both affect truth, religion being related to philosophy in some sense? And then more specifically, how can a biblical view of the cosmos relate to our modern scientific view? This is another entire lecture series we could have on this, but I think it's helpful to remember that science is very good at asking questions of how things work. How do they work physically? When in natural history? Why in terms of physical cause and effect? The tools of science are wonderful for that. The tools of science are not great at addressing bigger questions like why, capital W? Is there a purpose for all of this? Is there a God? How should we live our lives? How do we establish justice? These kinds of things, we need different tools. So a lot of times the confusion can be meted out by making sure we're using the right kind of tool to answer the right kind of question that fits with that tool. Here's some more perspectives. Again, Freeman Dyson, the famous physicist, says, why are we here? Does the universe have a purpose? Whence comes our knowledge of good and evil? These mysteries and 100 others like them are beyond the reach of science. Francis Collins, the geneticist, says we cannot discover through science alone the answers to the questions, why is there life anyway? Again, the capital W, why, not the mechanics of where life began, but why in terms of purpose, and why am I here? The National Academy of Sciences had a perspective that says religions and science answer different questions about the world. Whether there's a purpose to the universe or a purpose for human existence are not questions for science. Science is a way of knowing about the natural world. It's limited to explaining the natural world through natural causes. Science can say nothing about supernatural, and for example, whether God exists or not is a question about which, according to them, science is neutral. Now, not all scientists would agree with that statement, but that is at least one helpful approach. And I like this one from Sir John Polkinghorne, who's a physicist who became an Anglican priest in England. He said, he was the president of Queen's College for a while in Cambridge. Science and theology are both concerned with the search for truth. In consequence, they complement each other rather than contrast one another. Of course, the two disciplines focus on different dimensions of truth, but they share a common conviction that there is truth to be sought. And I think that's quite interesting because there are many people in the world today who would say there really isn't such a thing as truth. And yet scientists and people of some faith traditions would actually share a conviction that there is a truth, different kinds of truth, but truth worth seeking. All right, so let's move on to some tough questions that again often go a little bit beyond what we can answer with our scientific tools. One question, what will the long-term future of the universe hold? I mean, it looks to us now like if the universe keeps on in its present course, it's going to keep expanding, and that expansion seems to be accelerating. Eventually the stars will burn out, the galaxies will cool off. It'll be cold and dark. Is that it? You know, we don't know right now. That's our current picture, but there may be something else going on. There may be a multiverse, right? Not just our own universe. So there may be other things going on that we can't quite fully understand right now. Let's get back into a philosophical question. Should we feel insignificant when we look at the vast universe and this possibility of a multiverse? Good question. It kind of depends on how you define significance. You define significance as being in the center of the universe. You're not. If you define significance as being long-lived relative to the universe, we're not. But think of significance in a different way. I think we are. The significance is the fact that we can actually look around the universe and perceive where we are and have this conversation. To me, that's incredibly significant. That's a philosophical question. So people can address this in different ways. Carl Sagan said, "Who are we? We find that we live on an insignificant planet of a humdrum star, lost in a galaxy, tucked away in some forgotten corner of a universe." Do you ever wake up and feel that way? Have some chocolate, it makes you feel better. But you don't have to perceive it that way. I just explained to you kind of the way I perceive it, is that we are incredibly significant. From a biblical perspective, our significance comes from God. The psalmist in Psalm 8, again, looking up at the heavens, probably didn't have as much light pollution as we have now, wrote, "O Lord, our sovereign, how majestic is your name in all the earth." When I look at your heavens, the work of your fingers, the moon and the stars that you've established, what are human beings that you're mindful of them, mortals that you care for them? Again, that feeling of insignificance, looking at the heavens, feeling insignificant. And the psalmist didn't even know about other galaxies and things like that yet. But he went on and said, "Yet you have made them," that's us, "a little lower than God and have crowned them with glory and honor. You've given them dominion over the works of your hands and have put all things under their feet." Now, our dominion on planet Earth has not always turned out to be a great thing, but I look at this as dominion in terms of knowledge as well. We have the privilege of studying the universe on a very large scale and a very small scale. What a great gift. And if you're a person of faith, you can view this as a gift from God, the gift of investigation, exploration, and understanding. That is a God-given gift of significance. There's more tough questions. I like to show how the universe is beautiful and active and marvelous and awe-inspiring. And yet, when we look around on our little corner of the universe, our planet, we don't see all beauty and wonder and loveliness, right? Why do the same physical processes that are needed to form the creation and sustenance of healthy conditions for life on planets like Earth? And in other words, we need things like volcanoes and plate tectonics and earthquakes that come from plate tectonics to recycle our atmosphere. Why do such processes also cause such pain, death, and grief? Or the common question, how can God's good creation be so good and so bad at the same time? Why would a good God allow these things? And what about what creatures, including humans, do to other creatures? Is this okay? Is evil real? For example, I have a real heart for animals, and it just tears me apart to find out, for example, and this is just a random example, that people go into herds of elephants that are very sophisticated creatures with very sophisticated and sensitive family groups and gun them down just for their tusks. All right? Is this okay? I don't think so, but why do we think this is wrong? Where does this come from? I don't have time to go into that lecture today, but I think the answer for Christians comes in the perspective of the incarnation. There's a most profound verse in the Gospel of John which says, "In the beginning was the Word, and the Word was with God, and the Word was God. And through this Word all things were made." And then it goes on to say that the Word became flesh and dwelt among us. This is the core of the Christian faith, that the God responsible for the universe is also participating in the universe and redeeming the universe. And there is a future in line for the universe that is one of hope. And so that is something that I think is one of the core messages of the Christian faith. All right, in my closing section, I want to introduce to you the idea that the universe always holds new discoveries, new mysteries, and new surprises. What are these mysteries that we're investigating now? Well, one of them is dark matter. We see the effects of this matter gravitationally all over the universe, but we can't quite figure out what it is because it doesn't shine light. What is dark energy? We now understand just recently that the expansion of the universe seems to be accelerating. Something's pushing it apart. We just call it dark energy, but we don't quite understand what this is. Are there planets like Earth outside our solar system? And could there be life beyond Earth on some of these planets? These are the hot topics in astronomy. We know there's hundreds of billions of stars in our own galaxy, and now we know there's hundreds of billions of stars, of galaxies beyond our own. This is an image toward the galactic center, again from a ground-based telescope showing many, many stars in the dust lanes. Only one star in our galaxy is our sun, but could there be other planets out there like Earth? Could there be life? It's a hot topic. Well, first of all, we look in our own solar system for evidence of life. Just today, this image was released from the Hubble Space Telescope. Now, the image here is of Europa, which is a moon of Jupiter. It's a very interesting moon. It's ice-covered moon. You see the cracks in the ice. This is an image taken from the Galileo probe. But around the outside of this is the Hubble Space Telescope image that's showing faint evidence of plumes of water vapor escaping through the cracks in the ice. All right? This is exciting because if these are real, so these are very crude observations, so we need to get more evidence. But if these are real, it could be a way of investigating this water that seems to be in an ocean under the ice crust on Europa. And where there's water on Earth, there's always life. Could there be water in the oceans there? We would love to look and see, even in our solar system, if there's microbial life in places like Europa. Looking beyond our solar system, we're starting to find planets orbiting other stars. This is an artist's impression of a real star system discovered with the Kepler Space Telescope that shows a star and 6 tightly orbiting planets around that star. These are what we call exoplanets, and exo means outside, so planets outside our solar system. The discovery of exoplanets has taken off. When I was in graduate school, the early part of my graduate school years, the number of exoplanets being discovered, planets orbiting other stars other than our sun, was 0. All right? And then over the years, the techniques, they have to be indirect mostly and very clever to detect planets around other stars, got improved. So to the point now where every year we can discover over 1,000 planets outside our solar system. It's hard to study these planets in detail because they're so small relative to their very bright parent star. But we're getting better and better than this at an exponential rate. And in fact, you may have heard very recently the announcement that there is a planet that seems to be Earth-sized, orbiting probably the closest star to our sun. All right? So we've been looking at very distant star systems, trying to find planets, maybe Earth-like planets, when the very closest star to our solar system seems to have an Earth-sized planet. That's Proxima Centauri. So Alpha Centauri and Proxima Centauri are stars very close, just a few light years away from Earth. Proxima Centauri is a small star. It's what we call a dwarf star, and it seems to have an Earth-sized planet orbiting in the habitable zone, meaning it's close enough to that parent star to be warm enough that it won't be all ice, but not so close that the water will have all evaporated away. So you bet we're going to study that system more and more, the better we can. All right? This is an artist's conception of what it might look like if you were on that planet around Proxima Centauri looking back at your dwarf star. How will we know if a planet supports life? As we get better and better at studying these exoplanets, we look at the atmospheres remotely. We don't have the capability to travel to those exoplanets yet, but we can look at their atmospheres and look at them and see if they have the same kinds of evidence that we would see looking back at Earth that show us biological activity is going on. We'd look for evidence of oxygen, because on planet Earth, oxygen is produced by the plant life. We look for liquid water, evidence of it, that it might be a habitable planet. We might see in the reflected light spectrum evidence of plant life. We might see other evidence of biological activity. Methane, for example, is a product of many of the livestock species we use around this planet. So we might find a bovine planet someplace else. But when you see all this evidence and see if it comes together to show us evidence of potential biological activity on another planet, we'd have to rule out other explanations for those observations. So science is an incremental process. If we find it, how would society respond to that detection of extraterrestrial life, simple life? Or what about advanced life? Or what if we don't find life? What if it seems that life is unlikely? How are different people groups around the world going to respond to this? That's the subject of an entirely different lecture, but it is a very interesting philosophical and sociological question. I'll just briefly touch on it. This has been speculated on for thousands of years. Even Greek philosophers, Epicurus said there are infinite worlds, both like and unlike this world of ours. We must believe that in all worlds there are living creatures and planets and other things we see in this world. Now he's using the word world a little different than we do, but you see, people were thinking about this a long time ago. Now when I look at this picture and I see these gentlemen sitting around thinking and contemplating, I wonder like who's doing their laundry and that kind of stuff. All right, what about Christian thought? This has been thought about in faith traditions. Here's what the Dominican Father de Noia said. He said, Christians have always understood that the entire cosmos is a creation of God, that any life anywhere is a divine creation. There would be absolutely no motive for scandal if scientists were to establish the existence of life. And in fact, the Vatican even held a conference on astrobiology a few years ago where they brought in scientists and theologians to really explore what's going on in science and what it could mean in terms of a philosophical and theological sense. This cartoon, by the way, came out of the Washington Post article describing this conference, so I thought it was a little humorous, but no offense here, but it is interesting. The Catholic Church is very excited, in fact, about the science of astrobiology. Theologian Ted Peters did a survey of several religious groups, as you can see here, asking them more about this science or the possibility of finding intelligent life, which is considerably harder than finding evidence of simple life. But nevertheless, everybody's curious about finding intelligent life. So he asked Catholics, Protestants, evangelicals, Orthodox Christians, Jews, Mormons, Buddhists, and those who identified as non-religious, whether their faith convictions would be undercut if we found intelligent life living on another planet. Would it cause you to have a crisis in your faith? And everybody he asked thought about it and said, no, it won't cause me a crisis. I can incorporate this into my faith perspective just fine. But then he asked them a second question. He said, what about these other faith traditions? How will they be able to handle this? And most people, I'm sorry I don't have the chart for that, but most people said, no, these other faith traditions will fall apart. Most of the religious folks felt that the non-religious people their worldview would collapse, because here we finally had proof of God because of these intelligent beings. The non-religious folks said, no, all those religious folks, their worldview is going to collapse because we finally see that, the universe is much bigger than just our planet. And everybody thinks that somebody else's worldview is going to collapse if we find life elsewhere, just not their own. So that's a sociological, interesting thing. All right, to close, how should we respond to this amazing universe? How should we? I suggest a few things. One thing is that we feel a sense of humility, awe, hopefully curiosity. Many of us feel a sense of praise. And I think we can also feel troubled in some sense by some of the harder questions that I mentioned a while earlier. Another practical response is that we know there's life on one planet at least, so we can care for our own planet and all its inhabitants as good stewards. It's a privilege to live on a beautiful life-bearing planet, and we share this planet with other people and other creatures. And I would say we explore and learn. This is looking back at planet Earth from the space shuttle and seeing the sunset behind planet Earth and seeing that fragile blue atmosphere, showing us both the fragility and the beauty of our own Earth's atmosphere and reminding us to take care of it. I believe science and discovery can lift the human spirit. This is my colleague Gladys Kober. She's an astronomer. She works hard on data from different kinds of telescopes, processing that data. But every year on her own vacation time, she goes on a mission trip. She's a Christian and wants to use her talents in this way. Here's a trip that she takes to an orphanage in a country in Asia where the kids in the orphanage here are children largely of martyrs, so they've had traumatic lives. But fortunately, they're living in a place where they have enough food and clothing and love. And so what Gladys brings to them is what they really want from her, which is to hear about space, all right? These kids, like all kids everywhere, want to be astronauts, and they want to learn about the universe. So learning about the universe and nature is something that can uplift the spirits of people when it's shared in a loving and productive way. Here's another student in a class I spoke to. This is a class of visually impaired students. So we brought them images taken with telescopes that were coated with tactile feeling so that a galaxy feels different to the touch than a comet, that feels different than a star or a planet or a nebula. And these students were very much enthralled. They were just as enthralled by the beauty of these images as those of us are who can view them with our eyes. People also get inspired in the lab. So I just mentioned this book for those of you who are interested in how you might be inspired by doing science in your faith. And Ruth Bansowitz from Cambridge, England, has put together a book interviewing lots of scientists, how they are inspired in their faith life by the life in science. So it's called God in the Lab. It's a book. All right. Beauty, remember I wanted the takeaway, if you don't take away anything else, you live in a beautiful and active universe. Here's another star-forming region. The visible and infrared light are both integrated into this image of Westerlin 2, this star cluster, where you can see a cluster of massive stars that's recently formed out of this beautiful gas that's still producing lower mass stars. You are part of this beautiful universe. We all live in a universe of wonder and a universe of life. So let us be amazed, awestruck, and thankful. And I thank you very much for your attention today.
Thank you very much. As the applause shows, we are all very thankful for your presentation. Geneva, this is one of these wonderful things of coming together. A few months ago, in exploring what words we wanted to have, came up with the word exploration. You could have not kicked it off for us in any better way.
Awesome.
And we're very thankful for that.
Yes.
We are going to allow a question and answer time. So if you have a question, please raise your hand and I'll bring you the mic. I know Arnie here, so I'll give you first shot.
Can the mathematics of astrophysics accommodate before the Big Bang idea?
Yeah, so the question is, can the mathematics of astrophysics tell us something about what happened before the Big Bang? That's such a difficult question because before implies a timeline, right? So, and yet if time as we understand it started with the beginning of time and space in this epoch that we call the Big Bang or inflation or that period, how do you infer before that? I think you can infer some potential physical conditions that might have spawned what we call the beginning of our own universe, and it may have spawned other universes. That's what this kind of multiverse theory is all about. But it's coming from mathematical theories like string theory, things like that. It's impossible really for us to observe in any meaningful way this kind of period. So I think the answer is yes. We can kind of infer what kinds of conditions might have spawned what we term as the beginning of our universe, if in fact there are other universes. But then you pull the question one step back and say, well, why are there conditions that spawn universes? You know, so there's still the philosophical question as well. So there you go.
No.
Yeah.
Need to hold both of these. Yeah, I was...
By the way, those of you who want to sneak out, if you just want to sneak up here and grab an image and run away, I won't be offended at all, right? You can do that. So, yes. Yes.
I was struck by a kind of tension, perhaps, between something that was said in the introduction to you and something you said toward the end of your talk. about the question, the sort of broad question, what the cognitive relationship is between the sciences and religious belief. And I just wanted to press you a little bit. I mean, not at all obvious to me why the sciences couldn't provide evidence that might bear on the question whether there is a God, and if so, what sort of a being he is. I mean, not that you can point your telescope up there somewhere and see some big dude, but maybe there are more indirect lines of inquiry.
Yeah. Okay, so that's a very, very good question, and I think science can inform us in some ways, because you can certainly ask specific questions. For example, there are biblical passages that allude to the Earth's being firmly unmoved and the sun moving across the sky. Well, now it's obvious to us that that's poetic language and wasn't meant to be scientific. And yet, for people, many in the day, they took that very seriously, and it's truly the science information that caused people to take another look and say, well, no, the science is telling us something different. And so I think science can tell us how the universe works, and that can inform us to some extent about the nature of God. Especially, I think it works best if you're already perhaps a believer for some other reasons, and then science can give you a kind of a better handle on the character of God. In my experience, it hasn't been so useful to try to use scientific observations to try to prove or disprove God alone, although there are scientists who would say you can use science to disprove certain visions of what God is, right? If the science would counteract that kind of God, let's say a God that is constantly futzing with physical laws, well, we don't see that happening in any regularity. That's not to say that there can't be occasional miracles. Science can't kind of speak to that, but in general, we don't see that. So, you know, you could then say that science tells us that at the very least, if there is a God, God isn't constantly changing the physical parameters of the universe. So that would be some way I could say that science could inform someone's belief about the nature of God. But I think it'd be very hard for science. So I think you could, you know, set up a kind of straw man God, if you will, and then see if science, you know, addresses that particular model of God or not. But then that particular model might not be what, if there is a real God, the real God is like. So you might just be addressing that particular model of God. So I think you're right that science is not without use in these kinds of questions, but it depends on exactly the kind of question you're asking, what kinds of answer you're going to get from science, if that makes any sense. So, thank you.
I can just talk loud. I just wanted to thank you for a terrific lecture. That was just informative and inspiring, and I really loved it. So thank you for coming and giving that talk. I want to ask you a question about the edge of the observable universe. So I'm an English professor, but I have a love for cosmology and astrophysics. It's about the deep field pictures that you showed, and this projection that as the telescopes get better and better and better, that we'll see farther and farther. I'm just curious, like with this, what I understood about that from some of the reading I did is that we actually think that we're not going to be able to see, at least I thought maybe a couple of years ago, that we weren't going to be able to see much further. Like we thought that we knew that there was a limit to what we would be able to see because of the speed of light and the size of the universe and the rate of expansion.
Yeah.
But has that changed, or what are you thinking now about where the edge of the observable universe is or will be when the telescopes keep improving?
All right,
that was
so
a really ill-formed question, but I hope you understood what I'm getting at.
That's a good question. So there's different ways of approaching this. One is that as we're looking farther and farther out with these kind of traditional style telescopes, that we are going to be able to see closer and closer to the beginning of the universe, but not all the way to the very beginning, and there's a reason for that. For example, this particular telescope, well, you can't quite see it now on this because the lights are on, but this future space telescope called the James Webb Space Telescope is an infrared facility. It's going to be able to see farther than the Hubble Space Telescope for a couple of reasons. One, it's quite going to be very sensitive, but it's also going to be able to see infrared light. And it turns out that as the universe is expanding, the light from the most distant galaxies from us, as it travels to us, it gets caught up in that expansion of space and stretched basically to longer wavelengths of light. So light that may have started from stars that were radiating invisible light or even ultraviolet light, by the time it gets to us over traversing this 13 billion years of stretching space, it's become infrared light. So you need an infrared telescope to see some of those earliest fragments of galaxies. But the earliest fragments of galaxies, even though they come from within the first 0.8 of the 13.8 billion years history of the universe, they're still not the earliest. Before you get galaxies, you have to have gas. Before you get gas, you have to have the components of atoms. Before you have the components of atoms, you're in a very hot situation at the very beginning, just after the beginning of the universe, when that burst of energy is transforming into subatomic particles and then eventually atoms as it cools. So you get these early epochs that won't be seen with these kinds of classical telescopes. You also have an epoch called the Dark Ages, basically, which is an epoch when radiation itself was not able to escape. You needed some cooling of the universe, some expansion before you can have the escape of radiation that allows us to see it now. We can see, however, slightly after the beginning of the universe, this radiation from that first escape of light, which we call the cosmic background radiation. And this is, to me, one of the most amazing discoveries that has ever been made in astrophysics, which is a prediction that if our universe, as we know it, has not always been here in some kind of steady state, if there was a kind of a Big Bang, that we should be able to see the remnants as the universe expanded, as the first light was able to escape from itself, basically, and be free to travel. We should see that last scattering, is what it's called, surface of light anywhere we look, still today. It should fill the universe, and we do. So this was discovered a few decades ago, Nobel Prize material, and now we've been mapping out not only that this radiation exists anywhere you look, this leftover radiation from the beginning of the universe, but we can actually see that it varies very slightly in temperature from this patch to this patch to this patch. Why does that matter? Well, if you have slight inhomogeneities in the temperature, then that allows pockets where the cooler material can start conglomerating a little bit easier under its own gravity, and you get the first kind of sites for gas and stars and galaxies to begin to form. And you can even correlate the patterns of this temperature variation across the sky from this background radiation with the distribution of galaxies we now have in the current universe, and see that they're correlated. So you can actually relate the distribution of mass that we now see with the radiation left over slightly after the beginning of the universe. So you can't see everything, and you can't see all the way back to the very beginning, but you can see these interesting little evidences slightly thereafter, which are absolutely fascinating. So that's about the best we can do right now.
Go over to this side here.
Well, this is maybe mundane, but dovetails on the back of that. It's something I've wondered ever since we started talking about looking back to the beginning of time, so to speak. I'm having a difficulty because the speed of light, as matter can't be accelerated past the speed of light, right? So we're talking about things that are 13 billion light years away. The light from that has taken that much time to get to us. And we also postulate that maybe the Big Bang all started out in one tiny spot. How did things get that far away?
Okay, so this is very, very hard to visualize, so I'm going to say it in words, but neither you nor I can actually visualize this. But the model that we tend to think of as the Big Bang as an explosion, like, you know, something that exploded and expanded out. And so then if you use that model, then the next question is, well, what's it expanding into? And where is that explosion? And what's in the center and all of that? So it's not a great model. It's helpful in some sense, but it's not a great model, because a better model is to think about the fact that the universe began everywhere all at the same time, that the Big Bang happened in all of space at the same time, and that's why we see the background, the leftover radiation from this everywhere we look, not just in one direction. We see it everywhere. And everywhere, all of space has been stretching ever since. It could be infinite in extent, just bigger spatial scales as time goes on. Now, does that make sense? No, okay, but that's a better model to try to struggle with than the explosion over there model. Another thing to keep in mind is that in this model, the universe is expanding and continues to expand. These very distant galaxies that we're looking at, we are seeing them as they were billions of years ago. We're not seeing them as they are right now. We can't. Since that light started its journey, space has expanded. These galaxies have moved much farther on, and in some senses, very real sense, the stretching of space is stretching faster than the speed of light. Now, that itself, you know, seems unphysical, but, you know, go read up. We can't discuss it right now, but the stretching of space can be faster than the speed of light, even if light itself and objects cannot move faster than the speed of light. What that means is that projecting forward is that more and more galaxies will have accelerated out beyond what we would call the observable universe, what we can see within the time frame that we have, the time span that we have to look back. And so that means that as we look vast times in the future, if the universe continues as it is, we will be seeing fewer and fewer galaxies. And so it's kind of, you can either view this as a very sobering thought or a very happy thought, that we're fortunate to live in an epoch when our telescopes are good, and yet we can still see galaxies pretty much toward the, you know, shining pretty much toward the beginning of our universe. Whereas if we hadn't had this telescope technology for another, you know, trillion years, then we wouldn't be seeing even some of the even many of the galaxies that we can now see, because they would have accelerated off our ability to see them. So.
You talked a lot about how telescope technology has kind of improved over the past 300 years. Where do you see telescope technology going in the near future?
Oh, that's a great question. So telescope technology is increasing in amazing ways. One is just detectors themselves. I mean, you have more power on your smartphone now in cameras now than we used to have in super professional telescopes. So can't just recording technology for cameras has gotten easier and better. Another realm of improvement is what we call light suppression technology. This comes into play when we're trying to look for these exoplanets that are beside very bright stars. You want, and this is kind of counterintuitive for an astronomer, but you want to be able to suppress the bright light from the star so that you can see the very dim stuff around it, and that's not easy to do. So light suppression technology is a very hot topic in telescope technologies. We want to be able to observe very sensitively, so that often involves putting telescopes in very delicate situations. The new James Webb Space Telescope is an infrared telescope. It's going to be observing infrared light from very, very distant faint objects. And so it needs to not be confused by heat radiation from its own mechanics or even coming from planet Earth. So this new telescope, I wish I had a better slide of it, but that's going to launch, you can kind of sort of see it in the lower there. It's got several layers of sun shields that have been developed to kind of shield the actual optics of the telescope from planet Earth and from the sun and from anything else that might send the slightest bit of heat its way. So you want it to be cool, cold for infrared observations. You want better recording possibilities for any wavelength of light. And I haven't even mentioned, but there's another whole realm of studying the universe that's suddenly opened up to us, which is called gravitational waves. So I don't know if you're familiar with this gravitational wave detection, but it's really exciting in astrophysics because one of the things that Einstein predicted in all his brilliance is that that mass actually distorts space. And so if you have some disruption or motion in especially, well, any mass, it will send a wave through space-time that's analogous but different to the radiation waves that we detect with telescopes, the electromagnetic radiation. These are gravitational waves. And so this is, predicted, but always thought to be extremely difficult, if not impossible, to ever detect. But nevertheless, detectors have been built to try to detect tiny distortions in space or space-time that would be indicative of a passing gravitational wave. And so the LIGO detector, earlier this year, that consortium made an announcement of the first detection of a gravitational wave. How you detect it is you have these very sensitive detectors that are measuring the time it takes for a laser pulse to travel between them. And if the distance changes ever so slightly, then the timing will change ever so slightly. And so you can say that a gravitational wave has passed through. But of course, to have a measurable gravitational wave, you have to have some phenomenal distortion of space somewhere out in the universe, which can mean things like two black holes merging together or something like that. And that is exactly what was detected. So now gravitational waves have become real, at least in our understanding, and building new and better detectors for gravitational waves is on the horizon to better understand the end states of stars and the centers of galaxies when these major events of massive bodies merging and things like that take place.
So much more to explore and have fun with and enjoy. And we thank you that you have given us a taste of so much more. And thank you also for coming. If you have a real pressing question, I'm sure you could come up briefly and ask. But thanks again for a wonderful evening.